So we're still rocking Gaussian elimination. Now, don't worry about the title, it's a bit hard to understand. Here's the problem. We have three planes here. Now, this plane is straightforward, x plus 2y minus z equals 2. But this plane here has like an a value in it, some number. And this plane here also has some number in it, a, some unknown a value. And the question is this: find values of a resulting in a unique solution, so that is these three planes meeting at a point. Infinite solutions, that is these three planes meeting at a line. And no solution, these three planes not meeting at all. So we're going to have to do Gaussian elimination with this tricky little a in here. So I'm going to put it into an augmented matrix first. So far, not much different to what we've done in the past, just this little thing here. Be careful, it's negative a plus 2, so negative a plus 2 goes there. This is a minus 5, so that goes there. Now, we're going to want to get rid of this and this, make that 0, make that 0. So I can do that by subtracting 2 times row 1 from this and adding row 1 to here. So let's just be careful about it. So 2 minus 2 times this, so that's going to be 0, that's what we wanted. 5 minus 2 times this, 5 minus 4 is 1. And now we come to this thing. Negative a plus 2 minus 2 times 1. All right, let's just write it out. Negative a plus 2 minus 2. All right, so that's plus 2. But that's negative a minus 2, that bit there. And then I'm adding 2 to it. All right, so I'm just left with like a negative a. And then 3 minus 4 minus 1. And then coming to here, negative 1 plus 1 is 0. A minus 5 plus 2. A minus 5 plus 2. That's a minus 3. And 1 plus negative 1, that's going to be 0. And 1 plus 2 is going to be 3. Alright, so now that we've done that, we need to get rid of this a minus 3. We need that to be a 0. Now, how are we going to do that? Well, if we were to take row 2 and multiply it by a minus 3, this bit here would be 1 times a minus 3, which is a minus 3. If I then subtract that from that, I'd get a minus 3 minus a minus 3, which is going to give me my 0 here. So, all that said, it's going to look like this. So down here, the new row 3 is going to be equal to the old row 3 minus a minus 3 times row 2. Alright, so stepping through it, we get a 0 here. We get a minus 3 minus a minus 3 times 1. So, a minus 3 times 1 is a minus 3. A minus 3 minus a minus 3 will be 0. And then we get 0 minus, we need to write this out, this is too confusing. 0 minus a minus 3 times negative a. Negative a times a minus 3. Alright, so that's 0 minus a times a minus 3. So that's going to be 0 plus. Alright, so just have to make a little more space there, but we get this a bracket a plus 3. Okay, so finally we've got to do this last one here, which let's just do a little bit of working over here. 3 minus, and then it's a minus 3 times whatever row 2 is. Now, row 2 is negative 1 times negative 1. Alright, so that's 3 minus 1 times a minus 3, which is the same as 3 plus a minus 3. Now, 3 plus negative 3 is 0, and we're left with this a on the end, so we're left with a. And that is the end, right? Because we have 0, 0, a number, a bracket a plus 3, a, and then we've got all of this other stuff, exactly how Gaussian elimination should be. So now that I've got it down into this form, I can then start considering what values of a will result in a unique solution, what values of a will result in infinite solutions, and no solution. So let's do the for a unique solution first. Now, for a unique solution, a bracket a plus 3 equals a. That needs to have a particular property to it, right? So we need to have just a number that's not 0 equal to something. And that could be 0, because we could have like z equals 0. But what we can't have is 0 equals 0, because that would result in an infinite solution. Or we couldn't have 0 equals 3, because that would result in no solution. So in other words, that cannot equal 0. Now, what would make a and a plus 3 not equal 0? Well, if a was 0, that wouldn't work, because that would be 0 times something, and that would give us 0. So a cannot be 0. Or a plus 3, for that to be 0, that would be negative 3. So a cannot equal negative 3. So for a unique solution, a cannot be 0 and a cannot be negative 3. If a is either of those things, we're not going to get a unique solution. But anything else will work. So if I put like the number 2 in here, I'd get 2 times 2 plus 3, which is 2 times 5, which is 10. 10 equals 2. So 10z equals 2, and then I can solve that and find out what z is. So this is the answer to my first step. For a unique solution, a cannot equal 0 and a cannot equal negative 3. Any other value is fine. Now, what about for infinite solutions? Now, for infinite solutions, we need a bracket a plus 3 equals a to be of the form 0 equals 0, because that's going to lead us to infinite solutions. So what can I sub in for a? Well, it's pretty obvious, right? For infinite solutions, a must equal 0. If I put a equals 0 in there, I'll get 0 on this side, which is what I want, and I'll get 0 times 0 plus 3, which will lead to 0 there. So for infinite solutions, I need it to be 0 equals 0, and to do that, a must be equal to 0. Finally, we come down here to for no solutions. So for no solutions, I need it to come up with some sort of like contradiction. So usually it looks something like 0 equals a number. I'll just write 0 equals number. So what can I sub into this that will result in this weird contradiction? 0 equals a number. Well, here I said I could have any value for a except for 0 and negative 3. And that would give me a unique solution. Here I said that for infinite solutions, a equals 0 will give me infinite solutions. But what about this negative 3? What does that do? Well, it becomes pretty clear when we put it in there. If we put negative 3 in here, we'll get negative 3 times negative 3 plus 3 equals negative 3, which will lead me to negative 3 times 0 equals negative 3. That means that 0 equals negative 3. Contradiction, no solution. So, for no solution, a equals negative 3. So, to cap it all off, if you're doing a question that looks something like this, run through your Gaussian elimination and then consider what these are supposed to look like. This is supposed to be a number equals a number. This is supposed to be 0 equals 0 for infinite solutions, and this is supposed to be 0 equals a number. Now, I've worked in this direction. You might find it easier when you do questions like this to work in this direction. Find out what gives you, say, infinite solutions. Find out what gives you no solutions, and then whatever's left over is going to give you unique solutions. That's a great question.